Hi everyone, this is a supplemental lesson in finding the derivatives of algebraic inverse functions. We are not talking inverse trig functions, nor are we talking about logarithms versus exponential functions. We are talking purely algebraic inverse functions. So we're going to start out with a review of some things that hopefully sound familiar to you from Algebra 2. Basically a review of inverse functions, starting off with the definition of a function. Remember that a function is a relation, a set of ordered pairs, in which each element of the domain is paired with one and only one element of the range. Hopefully that definition sounds familiar to you. Now, as you talked about and learned about inverse functions before, perhaps you recall there are three different representations of a function. The first one is that you can represent a function as a relation itself, and I'll provide you with an example of each of these. Remember that a relation is simply a set of ordered pairs. So for example, if you had the relation 5, 3, 2, 3, and -1, 0. So this is a function because it is true that each element, each x of the domain is paired with one and only one element of the range. Second representation would be that as a graph. And perhaps you remember a test that you learned to see if a graph is that of a function, the vertical line test. Hopefully that sounds familiar to you. And finally, it can be represented as an equation. So, for example, a simple quadratic function such as x squared minus 4. You probably then learned how to find the inverse of its function given each one of these representations. So remember, the first representation was that as a relation. And I'm sure you learned that if you have a function given to you as a relation, all you simply do is swap the x and the y values. So in the example I had provided to you, the inverse of that given function would have been 3, 5, 3, 2, and 0, negative 1. Alright, this brings up an issue that we will be talking about today, in that whereas the original given was indeed a function, once you interchange the x and the y so as to find the inverse, what you have in the end is not itself a function. Second representation, remember, was that of a graph, and here again you swap the x and the y and replot the points. On your graphing calculator, you do have the draw inverse function that will draw the inverse of any function that you have entered under y equals. Finally, if the function was given to you as an equation, and this is probably the one you did the most often, in order to find the equation of the inverse, you began again by swapping the x and the y values, and then you simply solve for y. So hopefully all that sounds familiar to you. Now, one primary characteristic of a function and its inverse, it jumped a page, sorry. There we go. Is that the domain of f remember that will become the range of the inverse. And I'm sure you remember that f-1 notation. Likewise, the range of the original function f will become the domain of the inverse, which very much makes sense given the way in which we found each of these inverses was by swapping the x and the y, the domain and the range. So this very much makes sense. But as we saw with that relation that I provided you as an example, once you flip-flopped the x and the y and found the inverse, that inverse was no longer, or that inverse was no longer a function. And that does become an issue. You cannot just assume that the inverse of any function that you start with is going to be a function as well. Really, the only type of functions that will have inverses that are functions also are one-to-one functions. And perhaps you learned that, I hope you did. A one-to-one function is a function in which each x is paired with only one y and each y is paired with only one x. It is a true one-to-one relationship between the coordinates. Now there are two theorems related to functions and their inverses. It skipped a page again. Seems to like doing that to me. There we go. The first is If a function f is continuous on its domain, then the inverse of f will also be continuous on its domain. Secondly, if a function f is differentiable at the point c, d, and if the derivative of f at c does not equal 0, then the inverse of f will be differentiable at the point d, c. Now you have to remember that if you have a point on an original function that is the ordered pair c, d, remember, once you find the inverse, the point on the inverse will be the point d, c. That's why they flip-flop. So let's talk about how to then find the derivative of an inverse function. Suppose that f is a function that is differentiable on some interval I. If f has an inverse f negative 1, then the derivative of that inverse, and you see there are two different notations that you'll see that are pretty common. You see the ddx notation of f inverse of x. Another way you'll see this represented, and perhaps more commonly, is f inverse prime, so the derivative of f inverse at x. That is simply equal to 1 over f prime of x. That's the basic rule you need to know. Pretty simple. Oftentimes, though, we'll be trying to find the derivative at a certain point. So suppose you have a point a, b on the original function f. Then the derivative of the inverse at b, all right, remember, if a, b is on f, then the point b, a is on the inverse. Alright, and remember, this number inside the parentheses in function notation is always the x value. So the derivative of the inverse at b will equal 1 over the derivative of the original function at a. And that's because a is the x-coordinate for that original function. Typically where people will get messed up is not so much in the rule that it's 1 over the derivative of the original function. It's problems in which they're dealing with ordered pairs and you need to find the derivative at a certain point. And they mess up, which coordinate is the x for which function. So as we work through the next examples, you're going to see some notations that I've found to make that are helpful, that hopefully they will be for you. So let's start with a really simple example, just of a linear function, 2x plus 3, and we're going to determine the inverse, the derivative of the inverse, and then we're going to actually find the inverse, like you did back in Algebra 2, and find the derivative of that sort of as a proof that this does work. Alright, so remember the basic rule that if we want the derivative of the inverse, remember that's equal to 1 over the original function, the derivative of the original function. Well, what is the derivative of the function 2x plus 3? It's simply 2, so your answer is 1/2. Alright, but let's actually go through it the long way as a proof of sorts. Alright, let's actually find the equation of the inverse. Alright, so we're given the function. If we rewrite it as y equals 2x plus 3, remember that to find the inverse we're going to flip-flop the x and the y and solve for y. So when we do that, we have x minus 3 over 2 as our function. So this is our inverse. Now we want to find the derivative of that. Now to do that, we might want to rewrite it as x over 2 minus 3 over 2. It'll make it a heck of a lot easier. The derivative then, you know, is 1/2. QED, quod erat demonstratum. Any of you future math majors out there in college, you'll find yourself putting that at the end of your proofs. It's Latin, quod erat demonstratum. It's Latin for it has been demonstrated. That's what mathematicians typically put at the end of their proofs. Just FYI. Alright, so I have 3 practice problems lined up for us to do. So hopefully as we go through these, you'll see how I have found it's a little bit easier to walk through these. If you keep your thoughts organized as you do your work, these really are not hard. The hardest part is just making sure you think about it clearly, and the more that you can organize your work as such, I think you'll find a good bit of success with these. So the first practice problem I have for us, suppose we consider the function square root of x, and we know that function to contain the point 9, 3, and we want to find the derivative of the inverse at 3. Now you have to remember, if the original function contains the point 9, 3, remember that the point on the inverse is 3, 9. That explains why this is a 3 in there. So we're finding the derivative of the inverse at 3. So the rule is it's going to be 1 over the derivative, and the question is at what x value? Well, you have to remember the x value of the original function was 9. So we'll need to find f prime of 9. Alright, so we need to do a little side scratch work and find the derivative. So if we think of that original function as x to the 1/2, our derivative is going to be 1/2 x to the negative 1/2, which we could rewrite as 1 over 2 square root of x, just to make it easier to evaluate it. F prime of 9 that we need is going to be 1 over 2, then times 3, because of course square root of 9 is 3, so we get 1/6. So we're going to take this 1/6, put it over into our main formula for finding the derivative of an inverse. So you have 1 over 1/6, which in the end is equal to 6. The mathematics isn't that hard. Again, you just have to sort of keep everything organized. So let's try another. This time we have a quadratic function, x squared plus 2, and we want to find the derivative of the inverse at 3. Alright, now notice they don't give you the entire ordered pair. Alright, you have to remember this 3. It is the x value of the inverse. It's going to therefore be the y value of the original function. Alright, so as we set up our problem for what we want to find, we know it's going to be f prime of something. The question is, what is that something? So what we really need to do is find the x value for that original function, and we do know though that the y value of that original function would be 3. So we can make use of the fact that we know the y value is 3 and set the original function equal to it. And we find that x equals 1. Now you might be asking yourself, well, why isn't also negative 1? Remember that these have to be functions. So we can't have like two answers if you want to think of it that way. So we do go with the primary, the principal square root. And that will be pretty common when you do come across these. Alright, so now we know we're talking about f prime of 1 that we need to find. We do need to find our derivative. So the derivative of this function is simply 2x. That's easy enough. We need to know f prime of 1. Well, that's just 2. So we're going to take that and put it up in place of the f prime of 1. And our answer is 1/2 in the end. And we have one more. This time we have a cubic function, 2x minus x cubed, and we're asked to find the derivative of the inverse at -4. Alright, so as we talked about before, that -4, it's obviously the x value of the inverse, and it is therefore the y value of the original. So if we set up what it is we're trying to find, once again, we don't know what that x value is. So we're going to approach it just like we did before. And we're going to make use of the fact that we know that -4 is the y value of that function. Now this is an equation that you obviously cannot solve algebraically by hand. You will have to solve it on your graphing calculator. Easiest way might be to let y1 equal -4. Let y2 equal the 2x minus x cubed, and then simply find the point of intersection. So if you go ahead and give that a shot, you should be getting that your x value in the end is 2. And were something like this on the AP exam, of course this particular problem would be on the calculator part of the test. So then we need to find our derivative. So we know our derivative to be 2 minus 3x squared. We need to find the derivative at 2. So that would be 2 minus 3 times 4 is 12. We get -10. So we'll put that -10 up in place of the f prime of 2. And our answer is -1/10. So hopefully you can see, if you do organize your work, it does make it easier. I have found it helpful over the years to write those little notes, x value of f -1 is the y value of f. Maybe that will help you. This is one of those things that I find textbooks don't do the greatest job teaching. But I sort of figured out several years ago, and ever since then they haven't been that bad. So hopefully this will be of help to you. I do have an extra practice worksheet that I don't know if it's posted to Brain Honey yet. It's one that I found online by a teacher by the name of Tom Tom Reardon, and it really is good. A lot of this stuff will show up on the multiple choice part of the AP exam every year. Probably not in the free response, but you can pretty much bet you'll have at least one of them in the multiple choice, and whether it's on the calculator or non-calculator will really depend upon the work that's involved. This last example, for instance, would be on the calculator part. Those other first two that we did, probably not. So it would depend upon the work that's involved. So hopefully this little lesson was helpful for you. Let me know. Please feel free to give me some feedback. And if you need to go back and replay parts of it, feel free to do so. It will stay up on Brain Honey probably for the rest of the year. Thanks a lot.